Going to start.
Okay. Okay.
Uh, okay, so today we have another round of our seminar, and our invited speaker today is Russell Avdek from Institut de Mathématiques de Jussieu, and he will tell us about invariants of codimension two contact submanifolds. The floor is yours, Russell, so please.
Okay. Yeah. Thank you so much for the invitation. Yeah, as Roman mentioned, I'll be talking about the topic for today is invariance of codimension to context of manifolds. And so really I'm gonna call these contact divisors. Yeah, contact divisor means I have some context manifold MC and I have a codimension to context submanifold inside of it gamma. And so maybe this, depending on who's in the audience, you might consider this to be a bit esoteric. So I'm going to spend a lot of time talking about examples and, of course, going over definitions. There's going to be two sort of main classical sources of examples. One are braids in R3, and the other one is lengths of complex singularities. Um, After I sort of go through a couple of basic examples, I'll talk about some sort of classical invariants which come up in these classical settings and how we can generalize them to an invariant of these divisors in the 2n+1 sphere in some kind of full generality. And then the rest of the talk is going to be about structural results for these new invariants. And at least so I found, I wanted to investigate these things because it's, as I said, naturally comes out of some classical stuff. And in terms of applications, we'll see that this thing actually behaves in some sort of really novel ways, which to me is quite surprising in high dimensions. So as a warning, if you're sort of not accustomed to these kind of concepts, it's going to be a lot of definitions, but the techniques are all going to come from my two best friends here, classical books of Milner, characteristic classes, and singular points of complex hypersurfaces. So let's get into the details. So the main objects of study are contact manifolds. And so these are going to be odd dimensional manifolds, dimension 2n+1, equipped with some hyperplane field of C, which is co-oriented and maximally non-integrable in the sense of Frobenius. So this means that we can write it as the kernel of a one form, satisfying this condition, alpha wedge d alpha to the n is greater than zero. And in particular, this means that the d alpha, this closed two form, is symplectic when restricted to this hyperplane distribution. So the easiest, the sort of most basic examples you can start with are when n is equal to zero, meaning m is one dimensional. Then the examples, the closed examples are always disjoint unions of circles. So it's just oriented circles, and there's no hyperplane distribution. The next sort of canonical class of examples, which generalize this, are what we call a standard 2n+1 sphere. And this is the usual sphere. I view it as the boundary of a disk sitting inside Cn+1. And I take the contact plane field to be the complex tangencies. Does tangent space intersect the uh, uh, complex rotation of the tangent space? And so this is a super classical kind of setup. I can also explicitly describe this thing as the kernel of this one form is given as x dy minus y dx. So this is very nice. It's sort of easy to write down. And to get some little bit of a more explicit description of something which we can see and feel with our eyes and our hands, we take the standard R3, which is the three sphere minus a point. And it ends up that this thing is isomorphic to was clearly it's diffeomorphic to R3, but the contact structure is explicitly given by, can explicitly be described as the kernel of this one form, dt plus rd theta. And so to make it even sort of more visually intuitive, here I have a picture which is ripped from some lecture notes of Patrick Mousseau. And each one of these squares represents the contact plane field based at a different point. And so this is an example we'll sort of want to understand a little bit for the next slide. And so what this saying is at zero here, I have the t-axis pointing straight up. And at the point 0, 0, 0, the contact plane field is just spanned by the x, dy directions. And when I emanate outward radially, the contact plane field twists counterclockwise. So it's always, if you're looking at my screen, looking at me, which hopefully someone is, then it's always sort of just this motion with your right hand twisting. Okay, so now I know some basic examples of contact manifolds. This sets up our main definition, which are contact divisors. And so these are codimension 2 submanifolds, which are contact submanifolds in the sense that the tangent space of the submanifold intersect the contact plane field is itself a contact structure on the divisor gamma. And I'm always going to assume that the normal bundle on these submanifolds are trivial, meaning that it has a neighborhood that looks like D2 times gamma. And there's some nice theorem which says that, unlike sort of Riemannian geometry where there's some moduli spaces, here everything is quite flexible. And you can always choose a neighborhood so that on the zero section, the contact plane field restricted to gamma is the tangent space of this disk, that's the normal bundle, plus the contact structure on this submanifold. Okay, so now let's get into examples in the n=1 case. If I have one of these divisors in a contact 3 manifold, this just means it's an oriented link which is positively transverse to the contact structure. And so these are very classical objects of study. There's some great notes by Atnayer, which I'll reference at the end. And so if I explicitly use this model where the contact plane field is given by dt plus r squared d theta, I'll notice that any braids around the t-axis are positively transverse to the contact plane field. So here I've drawn some examples in the r theta projection. So I see if anything is sort of rotating counterclockwise, it's going to be positively transverse to the contact plane field. In particular,
one small question. So do I understand correctly that in order to define this positive transversality, you want to ask about co-orientability of a contact structure?
Yes, it always is co-orientable.
Okay, good. Thanks.
Yeah. So everything is oriented. And so in this particular example, we want things sort of pointing transversely. I guess if if my hand is the contact plane field, it should point out in the sort of positive direction. And so our first example would just be this unknot, which is just the unknot in the projects to the unknot in the r theta direction, and it just loops around once, and it's an easy, friendly example. It ends up that it takes a little bit of work, but you can see that this thing is actually is isotopic through contact divisors to this picture in the middle, which instead of having just one strand, now it has 2 strands and a positive twist to it. And I claim that this is not the same, not isotopic through contact divisors to this picture on the left, which is 2 strands, except they have a negative twist, a negative crossing. So I'm going to call the unknot gamma and this different thing gamma prime. And so to prove that these things are distinct, I'm going to cook up an algebraic invariant and then just compute. So the invariant is defined as follows. So I take I always call a sigma to be a Seifert surface for the link. And then I can take, now the contact plane field is gives me like a vector bundle over the surface. I'm going to take a section of it, and I'm going to require that the section points into the boundary of the surface. So this can be made to make sense if we sort of look at this decomposition of the contact plane field along the divisor. So I take this Seifert surface, I take this section of some vector bundle over, I count the zeros, and I'm going to define the linking number to be this count of zeros. And we can just take for granted, hopefully, I'll give a sketch of a proof later, that this thing is actually an invariant of the contact submanifold. It doesn't depend on my choice of Seifert surface and my choice of section. So this is something, what I've written down is actually minus what is usually called the self-linking number, but I'll just call it L. And so yes, this is an invariant of the contact submanifold. And for braids, there's a nice formula which says this linking number is the number of strands minus the number of positive crossings plus the number of negative crossings. So for the above,
sorry, maybe one small question, sorry for interrupting. But you consider, so you mentioned that if gamma is different from gamma primes, you consider this codimension 2 guys up to what?
Up to isotopy through contact divisors.
Okay, I see. Yeah, thanks.
Yeah, so it's a really sort of more topological, not like differential geometric. Because I'm considering things equivalent if they're isotopy equivalent.
Sure.
Or isotopic through contact divisors.
Sure. Thank
you. Yeah, and then so now in these two examples, for this gamma, here I have one strand and no crossings. So this linking number is 1. And then over here, I have 2 strands, no negative crossings, and one negative crossing and no positive crossings. So this linking number is 3. So using this tool, this algebraic invariant, I'm able to distinguish these two contact divisors in the standard contact structure R3. Okay, so let's just review what happened. I took these two, we had these 2 knots, which are transverse to the contact structure. Then we cooked at this algebraic invariant called the linking number, and we showed that there's 2 knots which are smoothly equivalent, contact distinct because they have different linking numbers, and the difference of the linking numbers is only 2. So this is sort of our setup and our sort of main classical example. And the topic of today's talk is going to be generalizing this invariant to all contact divisors with trivial normal bundle in the 2n+1 sphere. And then when we extend this invariant to higher dimensions, we're going to see some pretty strange behavior. So for example, I can consider what happens if I take some contact 3 spheres inside of the contact 5 sphere. In this case, the difference, if I have 2 such divisors, the difference of their linking numbers is going to have to be a multiple of 24 rather than 2. And so now I can look at this pattern of what this sort of minimal modulus has to be. Here it was 2 for links in R3, then it was 24. And if I do this in higher dimensions, then I'm going to see that this modulus tends to grow pretty big. So for example, if I have some 19-dimensional spheres inside of the 21-dimensional sphere, then the difference of the linking numbers has to be a multiple of 95,800,320.
Yes, these are nice numbers, but how do you get them?
Yeah, that's going to be there'll be some theorems.
Okay.
And sort of what's shocking to me in the high dimensional case is that in these dimensions, if the linking in, for example, 3 inside of a 5 manifold and 19 instead of a 21 manifold, we'll see that if the linking numbers are different, then that means that the submanifolds have to be distinct as smooth submanifolds. So not even just, so obviously they're distinct as contact submanifolds. We'll prove that they're distinct as smooth submanifolds. And that's sort of a contrast to the 3-dimensional case where we can have 2 divisors which are smoothly equivalent, but are different as contact submanifolds as measured by this linking number. Okay, so that's sort of that's what we want to do. We want to sort of develop this invariant and see some interesting behavior in higher dimensions that contrast with low-dimensional case. Hopefully, we're well motivated. And we sort of, there's room to talk about some technical nonsense. So the technical thing we're going to have to talk about are formal contact structures. And so, what's going on here is we start off with geometric objects. We're going to pass off the homotopical types of objects. And so the formal context structure is a homotopical version of a context structure. So what does that mean? So before I had this subbundle in the contact case, which is a kernel of this contact one form, which has some special geometry. For the formal contact structure, I just take a subbundle, co-oriented subbundle, in a two form, not necessarily closed, just some two form, which has to be symplectic on the subbundle. And I consider these things equivalent if they're equivalent through homotopies of all the data involved. And so this ends up being equivalent to saying, this is sort of the definition is homotopy equivalent to this other definition, which is that I have a subbundle of the tangent space, codimension one subbundle with a complex structure in the subbundle up to homotopy of all the data involved. So when we pass from context structures to formal context structures, there's some loss of information, as is probably expected. It ends up that on the three sphere, for example, there's an infinite family of formal context structures. They're indexed by the integers. And it can be proved that there's infinity plus one context structures, which follows some deep results. If we go to if we're looking at the five sphere, there's actually a unique formal contact structure on it. However, it can be shown that there's infinitely many contact structures. So now we're seeing that when we pass from contact to formal contact, there's sort of increasing loss of information. And in general, computing these formal contact structures on a sphere boils down to computing some homotopy group of some homogeneous space. And this is done in the 60s by Massey and his student Bruno Harris.
So since you're dealing with homotopy information, why it's not okay to consider homotopy spheres and not homospheres?
Yeah, everything I'm doing today works for homotopy spheres.
Okay.
Yeah. So the ambient. So that I'm talking today about the standard context structure on standard S2n+1. You can do it for any context structure on any homotopy sphere, and all the results will still work.
Okay, good. Thanks.
Okay, so now we sort of we've seen these context submanifolds in R3, and we know that this formal context structure is. And now we're going to go up in dimension by thinking about by seeing some examples. And one of the most fascinating examples, or I think perhaps the most fascinating place to find examples of these context submanifolds is by looking at links of singularities. So I take some polynomial f in n+1 variables. I say f0 is equal to 0, and df at 0 can be 0, but it has to be non-zero otherwise. And associated to this setup, I get this link of this singularity, which I'll call gamma sub f. This is the variety f is equal to 0 intersecting the 2n+1 sphere in Cn+1. That should be Cn+1. That's a typo. And so I take these submanifolds, these links of these singularities, and it ends up that the complex tangencies of the link always give it a context structure. So here's some classical examples for in C for the unit. I can get examples in the unit sphere in C2 by just taking polynomials that look like z0p plus z1q. And the link of this thing is going to be a torus link in S3. And it ends up, I can bring it back to R3 by projecting. And what I'll get, for example, for like a 1,0 torus link is my unknot, which I'd previously drawn. For 2,2, I'll get this hop link with two components. For 3,2, I get this torus knot, and so on, which is a trefoil.
Is it correct? I mean, if I remember correctly, so this links of singularities lead to some special context structures in a sense that they are always time fillable and hypertext. Is it true? Am I right?
Yes. Okay. Yes. Yeah. So these things are really special. Yeah. So I'll give some sort of more examples to see what sort of crazy stuff we can find. when we look at, for example, just this linear polynomial um, uh, for in C, what is it? C4, sorry. Then this is going to cut out a 3-sphere sitting inside of a 5-sphere. If I go up in dimension, let's say now I'm looking at complex 4 space, and I look at the polynomial, which is z0 to the 2k plus 1 plus a bunch of zi squared. This is going to cut out a link which is smoothly a 5-dimensional sphere, but all of the contact structures end up being distinct. However, we saw that they are the same formal contact structure because there's only one on S5. So this gives us some interesting examples of 5-dimensional spheres embedded as links in S7. Here's an even more interesting classical example. I take this polynomial, which is z0 to the 4k plus 1 plus z1 cubed plus a bunch of squares. And these give me Milner's possibly exotic 7 spheres sitting inside of S9. So it ends up for these that the smooth structure on this submanifold is determined by k modulo 28. And this is sort of described in this beautiful survey by Herzebruck I'll describe at the end. And it can be shown in this paper of Morita, which is one of my motivations, that all of these formal contact structures on these 7 spheres are distinct for any k. So these gives like very interesting embeddings of 7 spheres into S9. And so we have these singularities give us this beautiful collection of examples of these singularities. And then also sort of for more coarse, like geometric topological constructions, in this paper a couple of years ago, I described ways to perform surgeries on these contact divisors and make more of them. In the same way that I can just take a braid and I can flip some crossings to get more braids in S3, for example. Okay, so hopefully we're motivated that we have that these objects are cool, and there's lots of classically interesting examples. And so now I'm going to take my my invariant, which I described, this linking number, I'm just going to upgrade it to all dimensions. And so in order to do that, I need to know this following fact, which is that if I take any submanifold in the 2n plus 1 sphere, which has trivial normal bundle, then it also has a Seifert hypersurface, where here I think the Seifert is misspelled, which means that I have a 2n-dimensional manifold of the sphere, 2n-dimensional submanifold, which is oriented and has boundary being the submanifold gamma as an oriented submanifold. So this is just like we're used to thinking about Seifert surfaces for knots and links in R3. The whole thing also works in all dimensions. So now what I do is I have my Seifert hypersurface for some gamma. I take a section of the contact plane field over it, and I require that this section points into the boundary, near the boundary. And using this section of the Seifert hypersurface, I can define the linking number to be just the sign count of zeros of this section. And so this is exactly the same as in the 3-dimensional, as the case of links in the 3-sphere, but just no one ever wrote this down for reasons I don't understand, and no one studied it. So this is our invariant, and to prove that it's an actual invariant, I'll sketch the invariance proof. So first start off with like, how do you build a Seifert hypersurface? So this takes a little bit of cohomological work, but it's not that hard. You take the n sphere, the 2n plus 1 sphere, minus the codimension 2 submanifold, and you build a circle valued function on it so that the inverse image of a regular value is exactly one of these Seifert hypersurfaces. So it's not super hard. And it ends up that if you sort of zoom in and zoom into the neighborhood, which looks like gamma times d2, then this function is going to just be the angle in the d2 direction.
Can you say that it's something like an open book decomposition in this case?
Yeah, it looks like an open book, but you can have some sort of Morse type singularities.
Sure.
And so yeah, so here the regular values aren't always going to be so you'll have some sort of modification of them. But what happens is now if I take a homotopy between two such circle valued functions, or I can change the regular values, this is going to give me a cobordism between the two inverse images of regular values. So it's a cobordism on a manifold with boundary. Okay, maybe a little strange, but because we have like absolute control over what the function looks like through the boundary, the cobordism is just trivial near the boundary. Okay, so now I have these Cypher hypersurfaces exist, and I can show that they're all sort of cobordant. If I take these any two such hypersurfaces constructed in this way, and I take sort of homotopies of sections between them, this is going to give me an oriented one-dimensional cobordism between the zero set of one section to the zero set of another. And now I have two collections of oriented points which are cobordant. This means the sign count of points is the same, and that's the proof. So that's the proof. And one thing that we noticed, one was sort of nice observation that we picked up along the way, is that because we have cobordism invariants of these Seifert hypersurfaces, when the dimension of this Seifert hypersurface is a multiple of 4, this means that the signature of the Seifert hypersurface is going to be an invariant of the smooth link gamma. And so there's other ways to build this using like Alexander modules and some classical stuff as well, but this is a very easy way to see it. Okay, so now let's see what happens in the case of links of singularities. For singularities, I have this function f, whose zero locus intersecting the sphere gives me my context set manifold. In this case, I can build my circle value function to just be f divided by the modulus of f. That gives something called the Milnor fibration. Each fiber of it is naturally a Seifert hypersurface, which is called the Milnor fiber. And it's non-trivial to show that this Seifert hypersurface has the homotopy type of a wedge of spheres of dimension n. If it's half the dimension, the dimension of the spheres is half the dimension of the Seifert hypersurface. And so this number of spheres is called the Milnor number. And so in some cases, we know how to compute these Milnor numbers really well. For example, all the singularities I described in the previous, or maybe 2 slides ago, are they're what we call Bryce-Horn-Pham singularities, meaning they always look like Z0 to the A0 plus Z1 to the A1, et cetera, et cetera. And in these cases, there's a nice formula for computing. So this Milnor number is super important to algebraic geometers and people thinking about singularity theory. And for this invariant, the linking number, it ends up just equaling the Euler characteristic of this Milnor fiber. In particular, it's just 1 plus minus 1 to the n times the Milnor number. So for singularities, it just captures the same exact information as the Milnor number. So now hopefully we have some intuition on what this linking number is doing. One, it generalizes some kind of writhe for braids to higher dimension. 2, it generalizes this Milnor number from singularities to all contact divisors. And 3, we can imagine, okay, as this number sort of goes up in absolute value, we're having more complexity. So for example, we saw that there's things which have linking number 1, which are sort of standard spheres embedded into standard spheres. Well, we can have some really complicated singularity, which gives me like a different embedding of a smooth sphere into a sphere. Okay, so now I have this, I sort of know about context submanifolds. This linking number, we have some examples, and then we're going to go back to our original example. Our original motivation was we have some knot, some contact knot in S3, and I can modify it locally while keeping the smooth knot type and changing it so that this linking number goes up by just 2. So to qualitatively summarize, we see that there in dimension 3, there's lots of these divisors gamma, which are smoothly equivalent, distinct as contact divisors, and close to each other as measured by L. Close meaning that 2 is a small number, which I guess is subjective. So the rough question is, I want to know, can I see these same kinds of examples in high dimensions? And to extract a precise question of this, I can ask, if I have 2 of these contact divisors in S2n plus 1, and they have the same formal contact structure intrinsically, how big does this difference in linking numbers have to be? So I could ask the same question for contact structures, but it's sort of a little bit too specific. So I'm going to use this formal contact structure. So how big does this difference in linking numbers have to be if I have 2 divisors which are intrinsically equivalent? Okay, and then so to state what the theorem is, I'm going to need some definitions, which coming from cobordism theory and computing Chern numbers and stuff. So, so to state how big this difference in linking numbers has to be, I'm gonna talk about complex and complex spin cobordism groups. So I'll say that omega U2n are the cobordism classes of stably complex manifolds of dimension 2n. Similarly, I have this space omega CS2n, which are stably complex spin manifolds up to cobordism. And I'm going to define 2 numbers, Cu2n and Cs2n, which are the greatest common divisor of the top Chern numbers, Cn, over these manifolds, restricting to those submanifolds for which all their other Chern numbers are 0. So, okay, maybe that's a mouthful, but we'll see some explanation in a minute by working out examples. So when 2n is equal to 2, I know that the cobordism ring is generated just by CP1, right? And its top Chern number, C1, is just the Euler characteristic, it's 2. Okay. Now let's go to real dimension 4. Here, there's 2 Chern numbers. There's C2 and there's C1 times C1. To make C1 times C1 vanish, it imposes some relation. And that means that the manifolds which I'm interested in are always cobordant to some number of copies of 9 CP1 squared minus 8 CP2. So this means that this the integral of C2 over this formal sum of manifolds is 12. And this means that this number, Cu2n, is 12. However, I can't make there's no real 4-dimensional complex spin manifold which has these types of Chern numbers. If I require the spin condition, then this minimal number is 24, which is the C2 of the K3 surface. So this is sort of imposing some Calabi-Yau condition. If I go up again, I know that the 6th sphere is an almost complex manifold because it's the space of unit imaginary octonions. So you can show that it has an almost complex structure. And its top Chern number is 2. So I know that my first set of numbers are 2, 12, 24, and 2. And I keep computing. And I sort of have some theoretical bounds on what these numbers should be.
Is there a reason? Yeah, sorry for interrupting. Is there a reason why? So in this table, whenever both numbers are there, so the one to the right is twice the one to the left. Is there a reason for that?
Well, actually, most of the time they're the same. And then in cases when the 2n is 4 modulo 8, then it appears the theoretical bound gives it as multiplied by 2.
I see.
Yeah, and then so there's a reason for that having to do with some stuff about complex spin boardism. But anyway, so that I wrote some computer software. So I have some by hand calculations, and I wrote some computer software, and I have some theoretical bounds, and I know what these numbers should be, and I have a conjecture what the numbers should be, but I don't know how to prove the conjecture. So if someone in the audience knows a lot about computing Chern numbers, then please let me know. But anyway,
can we state this conjecture as your conjecture?
oh yeah, no, I don't think it's hard. It's probably not hard enough to be an interesting conjecture.
I'm just kidding. So, yeah.
But I'll state what at the end. I'll state what the bounds are, or what the conjecture is at the end of the talk. But anyway, just kind of looking at the table, we see that the number tends to grow pretty quickly, and it's like some interesting pattern. So started off with 2, which is the relevant number for contact submanifolds of S3. We get to to tens of millions pretty quickly. Okay, so now I know what these numbers are. I'm ready to state my theorem, the first main theorem. So the theorem says if I have, remember our question is we have 2 contact submanifolds. They're intrinsically the same formal compact structure. I want to know how big can the difference in the linking numbers be? And the theorem is if I'm in that situation, then the linking number, the difference of the linking numbers has to be a multiple of this Chern number associated to stably complex manifolds. And if moreover, the first cohomology of the submanifolds are 0, then the difference in the linking numbers has to be a multiple of this special complex spin number. So here's some examples. We already saw that we saw proof by example. It's an actual theorem that if I have 2 knots transverse to the contact structure in a 3-sphere, the difference of their linking numbers has to be a multiple of 2. And using this theorem, we can see that if I have 2 embeddings of the 3-sphere into the 5-sphere, intrinsically the same, then their difference in linking numbers has to be a multiple of 24. And so as I mentioned previously, 2 embeddings of the 19-sphere into the 21-sphere, the difference in the linking numbers has to be a multiple of 95,800,320. And so the rough answer to my question is, if the sort of dimension is large, the difference of the linking numbers has to be 0 or very big. And so as an applications, because I know that the linking number of these singularities, of the links of these singularities associated to an isolated complex singularity, is just in terms of basically the Milnor number. This says that if I have 2 links of 2 distinct singularities, and their intrinsic contact structures are the same, then the difference of their Milnor numbers has to be a multiple of this complex Chern number. And in most of the interesting n=2 cases and in all higher dimensions, this means the difference of the Milnor numbers has to be a multiple of this complex spin number. So this tells you that this Milnor number is a super classical quantity, and the theorem says that these contact structures provide some information, some algebra geometric information about what's going on. Okay, so now here's like a sketch of the proof of the theorem, and so again, it's all just using these Seifert hypersurfaces. So one thing I notice, and some sort of elements of stable complex topology. So one thing that I notice is that if I take the tangent bundle of the 2n+1 sphere and I stabilize it once, well, it's just the tangent space of Cn plus 1, right? So I can write this as R plus C is equal to the complex line plus C. And so if I just restrict this bundle to the Seifert hypersurface, this gives the Seifert hypersurface the structure of a stable, almost complex manifold. Right, because I just added some extra dimension to the tangent space and it made it complex. That's what the definition of stable, almost complex manifold is. So now here comes the interesting part. So what I do is I take some gamma and some gamma prime, 2 divisors, and I can glue their Seifert hypersurfaces together. So I make something I'm going to call sigma bar. And it ends up that when the formal contact structures on the boundaries the same, I can glue together the stable almost complex structures on the two Seifert hypersurfaces to make this sigma bar an almost complex manifold. So now I have this. Obviously, this is the thing I want to study and look at its Chern numbers. So I just glued together these two Seifert hypersurfaces, and I gave it the structure, this closed 2n manifold, the structure of a stable almost complex manifold. Now I can do a little bit of arithmetic with Chern numbers, and I won't explain the full.
Sorry to interrupt. When you say you glue, so how do you glue? I mean, you do it. It doesn't really matter how you glue it, or like you can just glue it in some way.
Well, like by definition, there exists some diffeomorphism which induces like a isomorphism of stable formal contact structures between them.
Right, but it's not unique, right?
No, not necessarily.
So it doesn't really matter how you glue it, just glue. I see.
Yeah, you just glue. Yeah.
Okay.
Yeah, so I take these two Seifert surfaces, I glue them. Well, it has to be in a way that the formal contact structures are identified. This allows me to put the formal the stable almost complex structure on this glued manifold. And then if we do a little bit of arithmetic, it's not too difficult to see that all of the Chern numbers, which are products of at least more than one Chern class, these have to integrate to 0 over this glued up manifold. And then now we know that all the Chern numbers on this manifold vanish except possibly for the top one. And then what I can do is I can look at the difference of the linking numbers, right? This is some sort of section of the contact plane fields restricted to each one of the individual Seifert hypersurfaces. So, I glued these, when I glue these things together, I'm able to glue these contact plane fields to some kind of hyperplane field of R plus the tangent space of sigma. And this difference in linking numbers just computes the Euler number of that bundle, which is this, right? So the Euler number of this bundle is the same thing as the Chern class of this bundle, which is the Chern class of this. All right, and then now we know, so this difference in linking numbers is the integral of this top Chern class over this thing sigma bar. Now all of sigma bar's other Chern numbers are 0, and that means that this difference in linking numbers has to be a multiple of this special Chern number. And so this finishes the statement. Or at least it tells you what the ideas are. And so so that's that. And then to get the spin statement, if the first cohomologies over Z2 vanish of the gamma, this means that so in any case, sigma and gamma inherit spin structures from S2n plus 1. And if under this cohomological condition, the spin structures are necessarily equivalent. And this means that I can equip this, I can make this sigma bar not only a stably almost complex manifold, but a stably complex spin manifold. And just building on the previous calculations, I know that the difference in those linking numbers has to be, it should say CS, it's the complex spin number in 2n of dimension 2n. Which establishes this statement modulo typos. So that's sort of the idea here. It's just some sort of gluing of some homotopical bundled data associated with these two, gluing the Seifert hypersurfaces together and keeping track of some homotopical data. Okay, so then this gives us our answer to our first question: is how big does the difference in linking numbers have to be? And now I think I'm running out of time, so I'm going to go quite fast. So now back to our original example. Remember, we found two contact divisors in S3, which are smoothly the same, but distinguished by their linking number. And what I want to know, my big question was, does this phenomenon hold in higher dimensions? And my first precise question was, how big can the difference in linking numbers be? My second precise question is, if we have the same formal contact structures on the divisor, but different linking numbers, can the divisors be smoothly equivalent? And so we see that that's something that can happen for gamma inside S3. I want to know, can this happen in higher dimensions too? And the answer is this gives an answer to the question. Remember that if I have the divisor has dimension 4m minus 1, then the signature of any of its hypersurfaces provides an invariant of gamma, which I'll just call the signature of gamma. And the theorem is, when I'm in this special dimension, which occurs half the time, gamma in a sphere of dimension 4m plus 1, then the linking number depends only on the intrinsic formal contact structure and the signature of the smooth divisor. So in particular, and then building on the calculation underlying this, is if I have two distinct contact divisors, possibly distinct, with the same formal contact structure, then the linking numbers being inequivalent means that the signatures of the smooth divisors are inequivalent, which means that the smooth divisors are inequivalent. So our question was, two contact submanifolds, intrinsically equivalent, like intrinsic contact structures are the same, but different linking numbers, can they be smoothly equivalent? And the theorem says that that's not possible when the ambient dimension is 4m plus 1. I can show that in the other case, when the ambient dimension has the form 4m minus 1, the answer is yes. But that requires some sort of constructions using those surgeries I said that I wouldn't talk about today. So that's sort of the answer to the question. And to me, this is like quite surprising. So to prove this thing, I'm going to introduce a new invariant, a new like sort of homotopical contact geometry invariant, which I'll call the Gompf-Merida invariant. And this associates to certain formal contact manifolds a rational number. And this thing is just a generalization of this invariant constructed by Gompf for certain contact free manifolds. As I also mentioned, this paper of Shigeyuki Morita from the 70s, he also ends up writing down the same exact formula underlying this, but he's only applying it to certain complex singularities in high dimensions. Okay, so to set up this proof, once I know what this invariant is, the proof is just going to fall out immediately. So I'll describe quickly how we can define this invariant. So here's what I need. I need a formal contact manifold of dimension 4m minus 1, such that all of its Chern numbers vanish rationally. We're actually going to be in a case where for the case of interest, we're going to have these things vanish over Z, but vanishing over Q is enough. So now what I do is I take some 4m manifold whose boundary is gamma smoothly, and then I want it to have a formal contact structure on R times sigma. And now I just want this thing, what I'm trying to set up is I want this thing to look like a Seifert hypersurface of a neighborhood of a Seifert hypersurface of some gamma. In particular, I want this formal contact structure to look like a complex line plus the formal contact structure on the submanifold along RT times the neighborhood of the boundary. So there's some formulas and stuff, but what's going on is I'm just making it look exactly like I'm studying Seifert hypersurfaces of knots in the sphere. And so now I have this 4m dimensional vector bundle over a 4m dimensional manifold with boundary. And so when I have a 4m dimensional vector bundle, the thing I'm supposed to look at is the L genus. So associated to any vector bundle, there's this polynomial in its Pontryagin classes called the L genus. And this famously comes from Hirzebruch's signature formula. So for example, Hirzebruch's signature formula would say, if I have a 4 manifold, then its signature is 1/3 times the integral of the first Pontryagin class. If I have an 8-dimensional manifold, its signature is the integral of this thing, which is 1/45 times 7p2 minus p1 squared, and so on and so on. But you can take this L genus, you can just define it for any vector bundle or anything. It ends up that in our case, we don't just have a real vector bundle. We have a vector bundle which is real dimension 4m, but is complex. And so when we have a complex vector bundle, this means we can express its Pontryagin classes in terms of Chern classes. In this particular case, this means I can take the top Pontryagin class, PM, and I can write it as 2 plus or minus the top Chern class. Now, it doesn't sort of matter if I'm on a manifold with boundary or whatever, I can make sense of a Chern class. And if I'm on a manifold without boundary, I can express the top Chern class as an Euler class, right? Now, this doesn't quite make sense because I'm working over a manifold which does have boundary. So what I'm going to do is I'm going to take my Euler class and I just replace it with this relative Euler number by saying, oh, I want to count zeros of some section of some vector bundle, and I need to impose conditions on the behavior of the section near the boundary of the bundle. So what I'm going to do then is I take this Pontryagin number in this L genus formula. I'm going to replace it with this relative Euler number and define the relative L genus to be just that. I just replaced one of the terms in the formula. And then I'm going to define this Gauss-Merida invariant of 4m minus 1-dimensional contact manifold to be this Pontryagin number, this L genus number, minus the signature. And so now what happens is, if you think about it for a minute, so I sort of define this thing using a particular choice of sigma, and it ends up that if I use any other sigma, the Hirzebruch signature formula and the additivity of the signature just tells me that this thing has to always be the same, independent of sigma and this vector bundle that I chose, this formal contact structure. So this thing is just an invariant of the formal contact structure on gamma. And so if you read this paper by Gompf, handle body construction of Stein surfaces, he writes this down for contact free manifolds, and he actually proves that it provides some complete invariant of the formal contact structure when coupled with some other data. Okay, so now I have my invariant. Maybe it's a sort of mouthful to describe what it is, but basically it's just you just plug in.
Sorry for interrupting. So once again, you mentioned that it's supposed to be so. In the case when m is equal to 1, namely the case of D3, the case originally considered by Gompf for the complete invariant of formal structure.
Yeah. So he proved in that, well, you need the Cohomology class of the first Chern class plus the D3 invariant provides you complete, assuming that the C1 is torsion.
I see. And in general, it's not supposed to be complete, right? So
if you have a non-torsion first Chern class, then this doesn't work. And,
I see.
And if you apply this to a contact sphere of dimension 7, I think, then you need this number plus you need one other like Z2 valued invariant to get the complete. To get the complete classification. So it doesn't give you everything, but it gives you almost everything.
Okay.
Okay. So now I have this D4m minus 1, and I'm going to use it to prove that if I have a contact divisor of the 4m plus 1 sphere, then this linking number depends only on the formal contact structure of the divisor and the signature of the smooth divisor. And building on that, if I have two divisors which have the same formal contact structure, different linking numbers implies different signatures, implies that they're smoothly distinct divisors. Okay, so let's now do the proof. It's very quick. So if I do the, assuming we sort of are comfortable with this invariant, so I'm assuming that my divisor gamma has trivial normal bundle, and if I sort of use just the product formula for Chern classes, the total Chern class of the tangent space of the sphere restricted to the divisor is a Chern class of a trivial line plus Chern class of the implicit contact structure. We see that all of the Chern classes of the divisor are 0. And this means that this invariant is defined. And so now, as probably you could see from the setup of the definition, I'm going to use the Seifert hypersurface, some Seifert hypersurface to compute this invariant. Right? So when I do this, I look at all the Pontryagin class of the sphere. They're 0 because it's just stably trivial bundle. And this means that in this L genus formula, there's only one term, which is just the top term, which is this relative Euler number. And so this, I just have 2 to the 2 plus minus 2 times this relative Euler number times this other thing, which is just a number that comes up in the L genus formula. So for example, it's for m is equal to 1, it's 1/3. And then the next one is 7/45, et cetera, et cetera. So now let's compute. My d 4m minus 1 invariant is that number minus the signature of the hypersurface. And so what is this relative Euler number? That's exactly the linking number. So I have this on the left-hand side. I have an invariant of the intrinsic contact structure. This is equal to an invariance of the contact divisor minus an invariant of the smooth divisor. So any two of them determines the third. Right? In particular, I have that this one in the middle, the linking number is just some invariant of the intrinsic contact structure plus the signature. So that establishes the first statement. And then for the second statement, okay, the difference in signatures is just is the difference of the linking numbers. So the linking numbers are different, the signatures have to be different, and the smooth divisors have to be different. Okay, so that's okay, so I'm like very close, but I'm very close to the end and very close on time. So I'm ready to summarize what we talked about today. So we took this invariance, we defined this, we very easily defined this invariant of contact divisors in height dimensions, and we see it generalizes this classical contact topology thing, the self-linking number for braids in like I say S3. It generalizes that, and it also generalizes the Milnor number of a complex, isolated complex hypersurface singularity to some very broad general context. And our first theorem was that if we have two of these contact divisors and they have the same formal contact structure, then we can say a lot about what the difference of their linking numbers are. And we also saw that for approximately exactly half of the dimensions of interest, this invariant only depends on the formal contact structure and the smooth divisor. In particular, just computing this thing, which is often easy to compute, allows me to distinguish smooth submanifolds. To say that equivalent formal contact structure means different smooth divisor. And so based on our example, first example of studying links in S3, we see that this invariant has very different behavior for contact embeddings in low versus high dimensions. And not only does the invariant have different behavior, but it actually shows us that the the sort of geometric topological objects are actually very different in different dimensions. And so, so that's a review of our main theorems. And sort of a bonus is if you sort of know what a formal contact embedding is, then you could do some sort of homotopy theory type calculations, and you can prove that if the divisor itself is a homotopy sphere and its dimension is not 7 modulo 8, then this linking number, there's this integer invariant, and the smooth embedding completely classify formal contact embeddings. So there's this folk theorem, which I've never been able to find a proof of, which says that the self-linking number and smooth type of a knot in S3 to completely determine the sort of formal contact embedding type of a transverse knot. And this generalizes that to all dimensions. And I will say that in this missing dimension, you need the self-linking number plus some Z2 valued invariant. So it can all be figured out. And okay, that's the end.
I see. Great. Thanks a lot, Russell, for the great talk. Are there any questions, comments, remarks? Russell, can you get? Yeah. I have a question. So basically regarding your second theorem, right?
Mm.
So as you said, so having different L's, right, different linking numbers implies that we have different smooth divisors. So somehow there is a difference even at the level of like a smooth submanifolds, right? Basically.
Yeah.
So,
This is assuming that they're intrinsically the same formal contact
yes,
structure.
yes. So my question is like, do you expect I don't know, some sort of like a refinement or slightly better invariants that could distinguish not just smooth divisors, but let's say seeing like different different like contact information on these divisors. Because here the difference is done like really using like you actually see the difference at the level of differential topology, right? Not at the level of contact geometry.
Oh yeah. You mean if I sort of pass from formal contact?
Yes, yeah, exactly. Yes, yeah.
So I can do some constructions and I can show that so this is the 4m-1 case.
Yes.
I can show in the other ambient dimension you can build smoothly equivalent divisors with the same intrinsic contact structure with different linking numbers, sort of generalizing the case of stabilization and for knots in S3. So those things do exist. And in this dimension, I don't know. There's definitely, in terms of like sort of characteristic classes and like homotopy theory, there's no more information can be squeezed out. But in terms of contact topology, like, yeah, you could start doing holomorphic curves. And so then it gets, yeah, I think there could be some. Yeah, I think after sort of that, then there's no more algebraic topology to do. I think everything would have to be using some Floor techniques.
Right, I see. So basically, you squeeze everything you could from algebraic topology. I understand.
Yeah. So yes, I think it's like there's more when it's like especially when you're working with spheres, like this last theorem tells you that there's nothing more to do. You can do if you want to work with divisors which are not themselves homotopy spheres, then it's like another level of complexity on the level of homotopy theory. Basically, you're trying to like it boils down to solving some like quite complicated obstruction theory problems. And I think there could be interesting things if people are interested in doing this to try to work that out. But yeah, other than this is I sort of what I originally wanted to do was I wanted to see can I take this transverse stabilization? Can I make a parallel thing in higher dimensions? And then it was like, okay, well first I have to figure out is the algebraic topology going to facilitate that? But beyond this, it's like you got to start doing contact homology and stuff. So
I understand. Okay.
Yeah.
Okay, great. Once again, are there any other questions, comments, remarks?
Oh yeah, and I'll just also put this. Yeah, if anyone actually knows anything about like, I think there's like formal group laws or something that could help about this. These are sort of the conjectures for what these numbers are supposed to actually be.
Oh, I see. Yes. Yeah, it looks nice. So you're writing it like it will appear soon on archive.
Yeah, it's I'm like sort of backlogged on a billion other projects, and I was like, oh, I want to do something short and nice and very
Sure.
classical. So
Sure. I
yeah,
understand.
and
Yeah,
no Hallmark for curves.
I understand. It was really nice. Yeah. No
Thank you.
holomorphic. Yeah. Okay. So, if there are no extra questions, then I believe we will close the session and we will stop the recording. Van, could you please stop the recording?